So next, we want to find the velocity and position functions on two ramps, from timing of the two ramps to opposed ramps, and then find the x1 and x2 functions. And finally solve, not finally, but solve x1 equals x2 to see where the balls should cross. Now you observed where they cross. Take the two functions and see where the two functions tell you they cross. Okay? And there's information here, but we know how to do this. We've seen it in class. So we kind of went through it. But we obtained our two position functions. For the sample data that I was using, we found slopes of 2.5 centimeters per count squared and negative 3.45 centimeters per count squared, just using the usual analysis with our graph and so forth, or using the symbolic expression that we derived previously. And then we have a C1 and a C2. Assuming our first ball started at position 0, we know that x of 0 would be 0, assuming the time is 0, making the usual assumptions that I'm not going to completely detail right now. So we found that C1 was 0. Similarly, x2 when t was 0 is 55 centimeters, so that C2 is 55 centimeters. And now here are the two x of t functions, so the task was set the two equal, write the equation, solve for t, find x1 and x2, and we'll also find v1 and v2. Now that's, for this data, and then you're asked to do it for your own data. For the data that I was using, these are the two equations. This is x1 of t, this is x2 of t, as we've seen. Set them equal, and then we add 3.45 centimeters per second squared times t squared to both sides, divide by the coefficient of t squared. That t is going to be plus or minus the square root of that result. And here we get, this is about 9, and the units will be centimeters divided by centimeters per second squared, which is second squared. Make sure you understand the fractions. And that's plus or minus 3 seconds. So that's what we obtained from this data. And most people got information fairly close to that, because of course for the sample data I was using some data from the observations. Okay. So why do we get plus or minus 3 seconds? Well, here's the actual motion, the x versus t motion. This is x versus t. I didn't label it, I just explained it. But you get these two parabolas for these two functions. The rest of the parabola goes into negative time, and of course the thing wasn't moving for negative time because you started the clock when you released it. It wasn't moving before you released it. In general, though, you could have a situation where you have motion before the t equals 0 time. For example, a ball is going up the ramp, and you don't start the clock until it starts back down the ramp. Well, it was going up the ramp, so here it goes up the ramp. Okay? Here's your position versus time. And from, let's say, negative 3 seconds to positive 3 seconds or whatever. Well, actually the 3 seconds is where the two graphs intersect. This is equal to this, where this graph intersects this graph. If you extend the parabolas, and my point here is that you get a point of intersection on this side. And what you get on this side, since these parabolas have their vertices on the y-axis, should just be a reflection of through the y-axis of what you get on this side. I didn't quite draw it that way, but that's the way it should come out. Okay. Now, we then went to the vernier interfaces, set them to collect 50 measurements per second for 10 seconds. And people didn't and make a sound, when the ball starts, when it stops. Make sure there's a sound that's synchronized with the starting and the stopping as best you can. And set to collect 50 measurements in 10 seconds. Now often the sound was a metal on metal sound, And sometimes we didn't get a spike at 50 measurements per second because the sound didn't last very long, and it just didn't happen to get picked up. So we went to 200 measurements per second. Everybody got the data and got it rather easily, and saw how we can get very accurate determinations of when those two sounds occurred and the time interval between the two sounds. That doesn't ensure that the sounds were actually synchronized with the two events that we were trying to time. And in fact, the way this was done, usually, that wasn't exactly true, so you can't take all that data to represent exactly what you were trying to measure, but it's still going to give you pretty good results. Okay, we'll talk more about that phenomenon later. Now there's something here that kind of summarizes a lot of what we do, so I want to talk about it.